In the previous lecture, we considered steady-state processes in various engineering equipment, and we applied the equation for first law for a control volume to such steady-state flow processes. In this lecture, we look at transient processes. Examples of such transient processes include charging or discharging of a tank. Let us consider an example of charging of a tank. So consider that there is a supply line through which a fluid is flowing. This could be a gas, or let's say in general a vapor. To this supply line there is a tank that is connected through a valve, and let's say that initially, let's say at t equals to 0, this tank is evacuated. Now this valve is opened and this tank fills up with this gas, and let's say that up till time t, the mass of the gas that has filled this tank is m. So once mass m of the gas is filled in the tank, the valve is closed. Now let's assume that this tank is well insulated and there is no heat transfer to this particular tank. And in this case, if we want to apply the first law to this tank, let's consider a control volume given by this dashed line. So this will be our control surface. Clearly, if the tank is rigid, then there is no work, and this work is work except the flow work. So there is no work done on this particular system. Now we are interested in relating the state of the gas in this tank at time t to the state of the gas at these inlet conditions, and let's call these conditions at inlet, and these conditions are same as the condition of the gas in the supply line. So what we want to do is that we want to see that if the inlet conditions are given, then what would be the condition of or the state of the gas at time t within this particular tank. So, and in our analysis for such problems, we can again ignore kinetic energy and change in potential energy, because kinetic energy and potential energies are typically very small compared with the change in specific enthalpy. So when we look at the first law, the change in enthalpy would be much larger than the change in kinetic energy and potential energy. So we'll ignore the effects of kinetic energy and potential energy in our analysis. Now, if we want to analyze this problem using the first law for the control volume, we'll have to make a certain set of assumptions. So the first assumption that we are going to make is that at any time instant, let's say at any time t, the state of the gas is uniform within the tank. That is, while the gas is filling up the tank, at any point within the tank, the properties of the gas are same. So there's no gradient in any property within the tank. And the second simplifying assumption that we're going to make is that the state of the gas at the inlet remains constant with time. That means any property that is evaluated for this inlet condition I, then those properties are not going to change with time. So with these two simplifying assumptions, we can now apply the first law for the control volume to this process. So the first step is to apply conservation of mass. So if you consider mCv denotes the mass of the gas within the tank at time t, so dmCv by dt is equal to the mass flow rate of the gas into the control volume. And note that there is no exit to this control volume, so mass can only enter this control volume. Also note that initially the tank is evacuated, so mCv at t equals to 0 is 0. So this is one equation that we'll need for our analysis, and this comes from the principle of conservation of mass. Next, let's apply the first law to a control volume. Recall that the first law in a general form for a single inlet and exit is given by this equation. Now, in our case, there is no mass flow out of this control volume, so this term is 0. Also, there is no heat transfer or no work done on this control volume that encloses this tank, so Q dot and W dot are also 0. Note that the left hand side is not 0 because the total energy of the gas within the tank is increasing over time. Also, we've neglected the change in potential energy and kinetic energy, so we can replace this total enthalpy only, and that means we have ignored the kinetic and potential energy contributions. So if we do so, our equation simplifies to dE Cv by dt is equal to the mass flow rate at the inlet times the specific enthalpy at the inlet. Now, this term ECV is the total energy, and we are looking at the contribution of only the internal energy, and we are ignoring kinetic energy and potential energy. And another assumption that we have made in our analysis is that the state of the gas is uniform within the tank at all times. Therefore, ECV is given by the mass of the gas at any particular time t, so E is also a function of time, times the specific internal energy of the gas within the control volume at time t, and we are assuming that the specific internal energy is uniform throughout the tank. Therefore, our equation becomes d by dt of mCv times uCv, both of which can be functions of time in general, is equal to m dot at inlet and specific enthalpy at the inlet conditions. Note that we have assumed that the inlet conditions remain constant with time. Therefore, Hi is not a function of time. So when we substitute the expression for m dot I from this equation over here, we get d by dt of mCv uCv is equal to Hi dmCv by dt. And hi is not a function of time because we've assumed that the inlet conditions are time independent. So we can also write this as d by dt of mCv times uCv minus hi, and that is equal to 0. Now, if we integrate this equation, what we get is mCv times the specific internal energy of the gas within the control volume minus the enthalpy at the inlet is equal to a constant. But recall that at t equals to 0, mCv is 0. Therefore, this constant is 0. What this means is that because mCv is not going to be 0 at later times, therefore to satisfy this equation, we must have that the specific internal energy of the gas within the control volume at any time will be equal to the specific enthalpy at the inlet conditions, which are same as those in the supply line. So this is an interesting result that for any given mass of gas within this tank, the specific internal energy of the gas within the tank will always be equal to the specific enthalpy of the gas in the supply line. Now, to make sense of this result, rather than using the control volume approach, recall that the mathematical equations that we derived for the control volume, that is for the principle of conservation of mass as well as energy, we in fact started from a control mass approach and we derived the general equations for the control volume, and those are the equations that we used and we have arrived at this particular result. But to understand why this result makes sense, let's go back to the original approach based on a control mass. Now, to look at that approach, let's again consider this tank that is connected to the supply line through a valve, and this tank is insulated. So now what happens is that at t equals to 0, this tank is evacuated. Therefore, if we consider a control mass of the gas that eventually enters this tank, then at t equals to 0, we can say that this control mass is somewhere over here, that is in the supply line. And for control mass, we are considering the mass of the substance of a given identity. So let's replace these boundaries by some virtual pistons as we had done earlier, just to signify that there's no mass transfer across these boundaries. Now you can think of this process of charging of the tank as, let's say that these pistons, they move and they force this gas into this tank, and eventually in the final state all of the gas is within this tank. So the whole control mass that was initially in the supply line enters this particular tank. Now we can apply the first law for a control mass to this control mass whose initial state was that it was completely in the supply line, and the final state is that it is completely within the tank. So within these two initial and final states, we can apply the first law for a control mass. So recall that if we ignore kinetic energy and potential energy, the first law for the control mass is given by delta U is equal to Q plus W. In this case, there is no heat transfer to this control mass, therefore Q is equal to 0. But there is work done, and work done on this control mass is because these pistons are moving and they are displacing this gas. So what is the work done? Let's say that after this tank is charged, the mass of the gas is m within the tank, and this mass, that is mass of the control mass, was initially in the supply line. So the volume that this control mass occupied within the supply line was, that is, m over the density at the inlet conditions, which is equal to the conditions in the supply line. So this was the volume, and let's call this as state 1. So this is the volume of the gas while it was initially in the supply line. So the volume is given by, of this particular control mass is m times the specific volume at the inlet conditions or the conditions within the supply line. Now, while this gas enters the tank, you can imagine that these pistons move and they push this gas. So what is the work done in this process? So the pressure in the supply line remains constant, and the work done on the system, and in this case our system is the control mass, is minus pi delta V, and this would be equal to minus pi times, so the change in volume is that the volume of this control mass within the supply line is reducing, and it reduces by amount minus V1. So the work done on this control mass is Pi times V1, and that is equal to Pi Vi times M. So this is the work done on the control mass. And now what is the change in internal energy? So initially the internal energy, let's say, is U1, and finally the internal energy, let's call it as UCV, that is, the whole gas is within this control volume. And in terms of specific internal energies, we can write this as M times the specific internal energy of the gas within the control volume, which in this case we are not looking at control volume, but we are using the same notation. So this means that the specific internal energy of the gas within the tank minus mass times the specific internal energy of the gas at the inlet conditions, that is equal to those in the supply line, and this delta U is equal to the work that is done on the system, that is equal to m times pi vi. So clearly this contribution of work, you can recall, is due to the flow work. So therefore if we cancel off these mass on both sides, we get UCV is equal to UI plus pi vi, and this is what we call as the specific enthalpy. So therefore, even if we consider a control mass approach to analyze this problem, we arrive at the same conclusion that the internal energy, or in particular the specific internal energy of the gas within the tank, will be equal to the specific enthalpy at the inlet conditions. So this example again shows that applying the first law to a control mass or a control volume would result in same conclusion. Only the mathematical formulation of the principle of conservation of energy is different for a control mass or a control volume, but the final result would be the same. You can use either control mass or the control volume approach to analyze the same problem, but for cases where we have this mass transfer to the system, it is more convenient to use the control volume approach. Therefore, the general equations for the conservation of mass and conservation of energy, that is the first law of thermodynamics, for a control volume that we have derived can be used to analyze such problems where mass is entering the system. But if you want to apply the first law for control mass, then you have to carefully choose the control mass which flows through the system, and then you need to apply the first law on this control mass as it flows through the system. But the final conclusions that you are going to get will be the same no matter which approach you apply. So with this, we have finished our discussion on the first law of thermodynamics. So we've looked at first law applied to a control mass, and then we looked at first law applied to a control volume. In the next few lectures, we are going to now discuss the second law of thermodynamics.